Electron configurations, a symbolic representation of how electrons are ordered within an atom. I can't tell you enough how important electron configurations are to our understanding of the chemical properties of the elements. 3 rules are used to determine the ordering of electrons within an atom. The Aufbau principle, Aufbau is German for ordering. Electrons fill atomic orbitals of the lowest available energy sublevels before occupying higher levels. So it always goes from low energy to high energy. And you'll see examples of this in just a minute. The Pauli exclusion principle. There is a maximum of 2 electrons in any one orbital, both with opposite spins, meaning spinning clockwise and counterclockwise. We can represent any orbital with a box. It doesn't matter if it's an SPD or F orbital. We use a box or a circle to represent those orbitals. And the arrows pointing in opposite directions just represent the opposite spins. There's no distinction between pointing up or pointing down. They're just pointing in opposite directions. Hund's rule. There must be 1 electron in each orbital of a sublevel before the second electron can be added. So if we were to look at the p sublevel, we would find that if we had 3 electrons, each one of those electrons would occupy 1 of the orbitals before a second one would be added to any of them. So go 1, 2, 3, 4, 5, 6. Hund's rule. Okay, now just watch this. Don't copy anything down. This is an energy level diagram with the energy levels n equals 1, 2, 3, 4, all the way to infinity. And you can see that there's a lot of overlapping that takes place. Like, let's look at the 4th energy level. This is 4s, 4p, 4d, 4f. And you have 4f, for example, higher energy than the 5s, even though the 5s belongs to a higher energy level. Well, according to the Aufbau principle, that doesn't matter. The electrons will always go to whichever is the lowest energy, and the energy increases as we steadily go up. So what I'm going to do here, and again, don't copy this down, just watch. I'm going to use gold as an example and add its 79 electrons in the correct sequence, following the 3 rules. So imagine that you have a gold atom, you've ripped off its 79 electrons, and now you're tossing them back one at a time. How would that go? Well, it would go something like this. The first 2 electrons would go to the 1s, and then the second 2 would go to the 2s. That's the Aufbau principle, always the lowest first, and then begins to fill up. Then the 2p, but Hund's rule tells us we'll have 1 electron in each one of those before we begin to double up. And then the 3s, the 3p, and then you might think it would go to the 3d, but no, the 4s is actually lower energy than the 3d, so it gets filled first. Then the 3d. 4p, 5s, 4d, 5p, 6s, 4f, and 5d, and then that's it. So that's the sequence. Now, of course, this would be a very difficult thing to draw. A simpler way to do this is what's called an orbital diagram. So let's look at that. Orbital diagrams. Uses boxes and arrows or circles and lines to show how sublevels are occupied. So it's just another way of representing what we just saw. Example. Draw the orbital diagram for nitrogen. Recall that atoms are neutral, so whatever the atomic number is, that's the number of electrons that we would have. So we have 7 electrons, and so we would need the 1s, 2s, and 2p. And then following the rules, 2 electrons in the 1s, 2 in the 2s, and we have 3 remaining. Each one would go into an individual p orbital following Hund's rule. Now that's a bit of a pain to draw. A simpler way to do it is using circle and slashes. It means exactly the same thing, but it's much easier to do. Now some of you write so small that you could hardly tell whether you have one electron or 2 electrons in the circle. So make sure that when you do this, you draw your circles large enough that you can see how many electrons you have. Sometimes kids write so small that just the thickness of their lead fills the circle. So please don't do that. Okay, now, nitrogen contains 3 unpaired electrons here. This is an important aspect in understanding an element's chemical properties. So what we're doing here has a bearing on where we're going. So it's not a minor thing. Nitrogen will almost always have 3 covalent bonds. And why is that? Because it has 3 half-filled orbitals to share with other elements. So when we get to our unit on bonding, we'll come back to that. Okay, again, just watch. So looking at nitrogen's orbital diagram, if we were to look at the energy level diagram, we see that they mean the same thing. So the first 2 electrons go to the 1s, so we can write it like that. Second 2, we can write it like that. And then 3 in the 2p, 3 in the 2p. So this is just a simpler way of representing what we're doing here. So remember, the ordering that we have for the orbital diagrams corresponds to the energy level ordering as we go from low to high energy. And that'll include all this crazy overlapping that we have. Fortunately, the periodic table is all we need to keep things straight, as you'll see. Okay, so why don't you try it? Titanium is atomic number 22. So when you pause the video and see if you can correctly put in the slashes necessary to represent titanium's orbital diagram. 3, 2, 1. Okay, now let me do it. And I'm going to just rewrite it down here. And again, use the energy level diagram to make sure that you're clear that they mean the same thing. So titanium has 22 electrons, so they would fill in like this. And then that's it. So now notice that these are being filled following the rules, the sequence of the rules. 2 more, and that's it. We also have 2 unpaired electrons that are important to note. Now, when you draw a sublevel, you have to include all of the circles or boxes that are part of that orbital. So here you might say, well, why do I need to draw these other circles? There's nothing in it. I only have 2 electrons. Should I just be able to draw 2? No, because the D sublevel has 5 orbitals. And as soon as you bring in one of the sublevels, you have to bring in all the orbitals that correspond to that sublevel, even if there's just 1 electron in it. Okay, now this, I'm just repeating what we just did, is a pain to draw, of course. A simpler way to do it, the more common way to do it, is called electron configurations. So the electron configuration for titanium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And this means exactly the same thing as the orbital diagram. So the 1s here, and then we have 2 electrons. So the 2 slashes here we represent by the superscripts there. 2s, 2s2, those 2 electrons are those 2 there. You have 6 electrons in the 2p, so there's the 6, and on and on. So it means exactly the same thing. So what we're going to be interested in is drawing the electron configuration for an element. Fortunately, there's an abbreviated way we'll get to called noble gas notation. Okay, note the maximum number for a sublevel is always the same. S, the maximum is always 2, P is 6, D 10, F 14. And that corresponds to the number of orbitals that we have in each one of those sublevels, with 2 electrons max in each orbital. So like the D sublevel, for example, has 5 orbitals, so 2 electrons in each one of those orbitals, 10. That's the maximum number. never go higher than these numbers, because it simply means that that sublevel is full. All right, now what we're going to be interested in doing is being able to look on the periodic table and immediately be able to determine what an element's electron configuration is. And it's not as difficult as you might think. Now, before I move on to the next slide, note that each period is numbered. This is the first period, the second period, the third period, and periods go all the way across. Fifth period, etc. All right, now let's take a look at a handout, a virtual handout that will be quite helpful. Okay, this is a handout that is on today's lesson module. It's called Electron Configuration. It's a PDF. I would encourage you to refer to this until you get real comfortable simply using the periodic table. This is the periodic table broken into its individual blocks. And you can see that each row represents an individual sublevel. So like this is the 4p block, but that's the 4p sublevel. The 6s block represents the 6s sublevel. The S blocks all have only 2 elements in each one, and that corresponds to the 2 electrons that are in an S sublevel. The P block has 6 elements, which corresponds to the 6 electrons in the P sublevel. 10 electrons in the D block, and 14 electrons in the F block. Now the goal here is to be able to determine an element's electron configuration based upon its location on the periodic table. So for example, this element right here would end in 3s1, 3s2. Element right here would end in 3p1, 3p2, 3p3. Now a couple of things to note. The S block elements and the P block elements all agree with the period that they're in. But the D block are all behind by 1 compared to the period they're in. So for example, this is the 4th period as we go across, which includes the 4s and the 4p, but the D's are all behind by 1. The F block elements are all behind by 2. This is the 6s, and then 4f, then 5d, 6p. Okay, now this is something that is best learned by example. So I would encourage you to refer back to this, but let's go right to some practice using just the periodic table. Write the electron configuration for the following elements and determine the number of unpaired electrons. So we'll look at these 4 elements. Carbon is atomic number 6, and so it's right here. And so it belongs to the 2p block. So this is 2p1, 2p2. So, but starting from the beginning, this would be 1s1, 1s2, 2s1, 2s2, 2p2. So that would be the electron configuration for carbon. We can double check that everything adds up right by simply adding together the superscripts, which in this case adds up to 6. And for the number of unpaired electrons, it's a good idea to take the last sublevel and write an orbital diagram for it, putting in the right number of electrons. So in this case, you have 2 unpaired electrons. Chlorine is atomic number 17, so it's right here. It's in the 3p block. So we have 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5. It ends in 3p5. Add all the superscripts, gives us 17. Again, just a little double check that it works. And then looking at the last sublevel to determine the number of unpaired electrons, we have 1 unpaired electron. Cobalt is atomic number 27. It is right here. So it is in the 3d block. So everything is filled up to that point. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 2, 3, 4, 5, 6, 7. And then looking at the last orbital, or the last sublevel, we have 3 unpaired electrons. For magnesium, jump the gun there. Magnesium is right here, so it ends in 3s2. It has no unpaired electrons. Its last orbital, or last sublevel, is completely full. All right, now this is a bit of a pain. Fortunately, there's a simpler way to do it using what's called noble gas notation. Noble gas notation, a method used to abbreviate electron configurations, almost always used. And what we do with noble gas notation is simply take advantage of the fact that each of the noble gases, except for helium, ends in P6. Neon is 2p6, argon 3p6, 4p6, 5p6, 6p6. Okay, so let's see how this works. Now, you don't need to copy this down, just kind of watch. You can copy it down later if you want to. All I have here are all the sublevels in the correct sequence, from lowest energy to highest energy. And I'm going to draw a line after every P, 2p, 3p, 4p, 5p, 6p. Now, each one of those lines corresponds to one of the noble gases. So 2p6 would be neon, and that represents 10 electrons. Neon is atomic number 10. And then argon is atomic number 18. Krypton 36, xenon 54, radon 86. You see at each one, the ending of its electron configuration would be p6. So krypton would be 4p6, xenon 5p6. So let's see how this works. Let's look at iron. Iron atomic number 26. So it's right here. So it ends in, this is 3d1, 2, 3, 4, 5, 6. So it ends in 3d6. So its electron configuration would be this. But using noble gas notation, we can shorten that considerably. So what we're going to do is use argon, because if we look at iron right here and just go backwards to the last noble gas, which is argon, we can use it to represent all of the electron configurations up to that point using argon in brackets. So argon in brackets is the abbreviation that we're using to represent all of the electrons, all of the electron configuration up to that point. But then we need to finish the story from that point on. So 4s2, 3d6. So again, all that we are going to do is just go backwards to the last noble gas, put that noble gas in brackets, and then pick up the story from that point. So let's do some practice. Oops, I forgot. Make sure you use brackets. Don't use parentheses. Only crazy, silly knuckleheads use parentheses. It's brackets. Write electron configurations for the following atoms using noble gas notation. Okay, so let's look at silicon. Silicon is right here. So if we go backwards to the first noble gas we come to would be neon. So we could put neon in brackets and then pick up the story from there, which would be 3s2, 3p2. Argon, now argon is in fact a noble gas. In the case that you have the electron configuration of a noble gas, we would always go backwards to the last noble gas and pick up the story from there. So it would be neon, 3s2, 3p6. Okay. Do not just write argon. Go back to the last noble gas and complete. Now this will be more relevant when we get our next lesson, when we talk about electron configurations for ions. Most ions, when they become ions, will have the configuration of a noble gas. You might remember the octet rule. Atoms tend to lose, gain, or share electrons to have the configuration of a noble gas. So it's a very commonality to have the configuration of a noble gas. Calcium is right here. So going backwards, the first noble gas we come to is argon. So argon in brackets, and then 4s2. And last, gold. Gold is right here. So going backwards, we would have xenon in brackets, and then 6s2, 4f14, and then 5d9. Okay, that is it for today's lessons.